Today talking about polymer phase behavior, and specifically today we are going to get into talking about how we could generate or how we can interpret and how we can create basically polymer blend phase diagrams. So we had a quick kind of review last time about material science and kind of your typical phase diagrams. We'll go through that again today. But the key thing here is to know that we're dealing with a single curve, which is that delta G free energy of mixing. So we'll get back to that in just a second. But anyways, let's go ahead and look and examine and create phase diagrams for our polymer blends. So one key thing again is that entropy of mixing decreases as your degree of polymerization increases. So high molecular weight polymers are less likely to mix. Again, we've kind of talked about that previously because again, your translational large polymers take up more spaces on your lattice. So the translational entropy, the number of microstates, decreases as molecular weight increases. So we have to kind of keep that in mind. And we should always keep in mind this kind of relationship between chi and 1 over t. So remember, chi has these kind of two forms that we've been working with previously. So one of those is the Hildebrand expression. So our monomer volume, Kt, solubility parameter 1, solubility 2 squared. Also, more generally in terms of energy, we had that it is equal to Z over Kt, and then energy 1, 2 minus 1/2. 1 minus 2 fractions. So when chi is large, again, monomers or our species 1 and 2 do not want to mix. When chi is low, they will, or negative, everything will always mix. And this kind of makes sense intuitively, right? So at high temperatures, things want to mix. If I have high temperatures, my chi is low. This inverse relationship should make sense. So we want to increase. And why should it want to mix at high temperatures? Because going back to this expression, as always, even if my number of microstates is low at high temperatures, this entropy term is going to dominate. We know that that entropy term always wants to push towards mixing, so that is what we're going to happen. So we want to have the chi value decrease, and then usually we will write this in terms of chi n, but that's going to be, we'll talk about that a little bit more when we talk about microphase separation. So we need to figure out what is the critical chi parameter where at different volume fractions materials will mix or will phase separate. So just to give some background, and let's look at first one type of scenario, which is polymer solvent solution. So if I'm mixing a polymer solvent, I could set x1 or x2 to equal to 1. So species 1 would be my solvent. So again, hopefully you remember back from chemistry, solute, solvent. Solvent will be the majority component. Solute will be the minority component. But here we're going to kind of typically talk about solvent in terms of molecules, so not polymers. So even if we have a larger volume fraction, that's what we're going to kind of always refer to as our solvent. So basically, we derived last time, and we showed quickly, but a little bit more quantitatively. In order to build our phase diagram, we need to figure out our conditions from Gibbs phase rule. So Gibbs phase rule, hopefully you remember from material science, degrees of freedom plus the number of phases equals the number of components plus 2. This is kind of your general for a assuming temperature and pressure constant. If you're looking at a single component phase diagram, so basically as a function of pressure as well, you could have this equation for your Gibbs phase rule. But anyways, the condition that we, if you remember back from our material science, if you read back through our OER, the way that you're able to define or basically obtain the Gibbs phase rule, how many number of degrees of freedoms you have depending on where you're at in the phase diagram. One of the assumptions is you make, aside from the Gibbs-Duhem equation, the first assumption that we make is that in order to be in equilibrium, in order to exist in two phases simultaneously, the chemical potential of every species in every possible phase must be equivalent at equilibrium. So what this is saying is that if I'm in equilibrium, if my species 1, 2, 3 are in equilibrium, my chemical potential of 1 is equal to chemical potential of 2 equals to chemical potential of 3 in whatever phase it's in. So if my chemical potentials are equal, then I'm in equilibrium. They exist simultaneously. It's not just we exist in a single phase. So multiple phases can exist at the same time, depending on, again, this Gibbs phase rule. So you can kind of double check and hopefully remind yourself from material science. But the physical interpretation. So what we're saying here is that the chemical potential is a change in free energy if we add or remove a molecule or a polymer or species. And what it's saying here is that when my chemical potential, when I'm at equilibrium, if I add or if I remove a species, the change in free energy is 0. So that is what is kind of happening here. If we're not at equilibrium and I change my species and I lower the free energy, then we're not at equilibrium. So that is kind of your statement for at equilibrium. So if I add a molecule, the change in that free energy is going to be 0. So they're going to be equal to one another. So you could also basically we derive the free energy of mixing, but as a little bit different from absolute free energy. So we can still use this equation. So I hope you remember this from chemistry. We can relate the change in the chemical potential in some system mu I naught, which is our your initial state. And we could relate this function to the activity. So again, that's kind of what we're doing. And last time we made this approximation that our chemical potential is essentially or very similar to the derivative of our delta G in mixing as a function of phi. We're going to see in just a second that there is one kind of additional chain rule step that we're going to have to make. And actually, we're going to see that in the next page. So again, these are derivations. Keep your high-level interpretation. So Ui is the chemical potential of the species in the final state, initial state, A is the activity. So I can figure out, and this is equal to my chemical potential of I can relate this to the derivative of Gibbs as a function of my volume fraction using, again, hopefully your old friend, the chain rule from math. So once you make this change and you take, basically we're going to take that derivative of delta G as a function of the phi 1, 2, whatever, from our delta G mixing from equation 46, we plug it in and you'll get to this expression here. So, and again, we assume where x1 is equal to 1 because one of our species is our solvent. So to build our phase diagram, again, we are saying that the chemical potential of all species in the coexisting phases will equal to 0, will be equal to one another. So in fact, this is what we've said previously right here. So if they're going to be equal to one another, we set them equal, and it is also described essentially our common tangent rule. So we're going to kind of see this visually in a second. I think that's going to really help. But again, if I'm in equilibrium, what it's saying, or what I can kind of see visually on my free energy curves, is that the slopes are equal. Because if the slopes are equal up here, my chemical potentials will be equal as well. So it's either, again, the same species in different phases, or this can be used to say this. So the delta G of mix of phi 1, for example, at some phi 1 that's equal to some, kind of special, phi 1 prime, some special place on your phase diagram, is equal to delta G mix of d phi 2 or d phi 1 at another special place in your phase diagram. So we're going to see this in just a second. So that is what we're working with. Again, if we're at equilibrium, we are going to be looking at a common tangent. So where the slopes in different phases or different materials, where as a function of phi 2 or as a function of mole fraction or number of monomers, the key thing is if I'm in equilibrium, my chemical potentials, my species are equal. And that is given by when the slopes are equal. We're going to see that in just a second. Actually, it's best visualized by a couple of graphs here. So let's go ahead and look back and remind ourselves of some phase diagrams. So let's go ahead and look here. This should look familiar, hopefully, from material science. So here I can draw, again, here I'm plotting it as a function of xb. This is basically equivalent to your number of molecules of B. If I want to plot the free energy at T1, this is just saying, and this should have some little slope, but if at T1 I'm all liquid, so the lowest free energy always wins. So my curve is just my liquid slope. My liquid line is lower than my solid line for all compositions of X here. Now, once I cross kind of over this region, I am liquid, and then I'm in this two-phase, basically solid plus liquid region here. So from 0 to x1 at T2, what phase am I? I'm liquid. So you see here the liquid line is lower. But as I start to go down, and I cross over into this two-phase region at T2 here, at x2, I can see that I have basically a common tangent here that connects basically the slope here and the slope here are equivalent. So when the slopes are equivalent, I could reduce my free energy below here. Again, it's better kind of shown like we did last time. So if I have a phase diagram like so, let's look at phase diagram like this. Temperature, excuse me, gives free energy, and I have a phase diagram looks like this. Temperature versus XP. I have my solid like this. Solid, my liquid. It's going to be liquid plus solid. So if I go from here to here, this is 1, this is 2. I know that at 1 and 2, I'm going to have a situation. So before, again, at this temperature star here, T equals star, my free energy initially in the right here from 0 to 1 and XB, I am pure solid. So I'm pure solid right here. This is switch here. Here I'm liquid. So pure solid, my slope here is low, and it's going to go up because afterwards from 2 right here to basically an XB value of 1. From 2 to the rest of the compositions, I'm pure liquid. So here I'm low here, liquid dominates, pure liquid phase, and then here. Between these two, I have my common tangent. So it's a little bit hard to kind of see in this diagram, but here it's clear. So I can lower my free energy by dropping here. So it is not worth it to be a pure solid here. Why? Because the free energy can be lowered if I phase separate. So the material is going to phase separate into a solid with some composition given here, a liquid with some composition given right here. And so it's going to phase separate into two phases in equilibrium. Why are they in equilibrium? Because my slopes are the same right here and right here. Now we don't know what the value of the slope is. It could be 0, it could not be 0. We're going to see for different polymer mixtures, sometimes when it's symmetric, it's going to be 0. Other times we're not going to know what the value of that slope is. The only thing we know is that if those two phases exist, or if we could find a common tangent, then those two phases are in equilibrium, governed by our kind of, again, this critical equation for chemical potential, which is that change in Gibbs mixing is just dT. So if these slopes are equal, then we're good to go. All right, so let's look at, that's our generic idea for material science when we have two kind of different distinct phases. Now, for polymers, it's a little bit different, right? So this is a phase diagram as a function of phi2, so our polymer, so phi2, and we're looking at different temperatures. So now you notice that we only have a single curve. Why? Because this curve is describing our equation for delta G mixing. That's it. That's what we're plotting here. So if we see a common tangent right here at temperature T equals T1, right here my slope is, or my curve is continuously concave up, and the value for delta G here will be basically negative. When that curve is completely concave up, when there's no changes in inflection points, I know that that material wants to mix. So it wants to be the lowest free energy here. There's no common tangents. It wants to lie on this delta G mixing curve. If I then look at different temperature, if I see a free energy curve like this, well, clearly I could see here there's a common tangent. Now, again, I don't know if this is, that slope is 0, but I know the slope here is the same as the slope here. So everywhere between phi1 and phi2, I can lower my free energy. I don't want to be on my mixing curve. I want to be in this phase separated state where some polymer or some solvent has a concentration here, and the other one has a concentration here, and that's what we're kind of working with. This phase separated state in equilibrium, two-phase region, phase separation. So everywhere in between here, I'm phase separated. So that's what is kind of being shown here. So here, you're mixed. Here, you're phase separated. In this kind of, again, and this line is a very, very special line. It's called, we're going to see, it's called in a second, the binodal. Typically, there will also be a spinodal here. But anyways, this kind of line is your coexistence curve. So along this line, I could simultaneously exist in the kind of phase separated and mixed kind of state here. The degrees of freedom are limited. Anyway, so everywhere along here, I could reduce my free energy by getting out. I don't want to be in the mixed state. I want to be in the demixed state. And the same thing here holds for temperature T equals T3. And you can see here that there's more concentrations that are in the demixed state. So as I lower my temperature, as I equivalently, because I know that chi is proportional to T, as I lower my temperature, as chi increases, as those interactions between 1 and 2 species become more unfavorable, there's going to be less region here where I can actually mix, where they will tolerate being next to one another. So, and again, that driving force is that translational entropy increase. So once I have that common tangent, that slope, I know everywhere in between going to be phase separated. It does not want to lie on this mixed curve. It wants to go to a demixed state. So next time, we are going to get into how do we calculate and actually create these phase diagrams. And specifically, looking back here, there's a critical temperature here where this is called Tc, and there's an equivalently a chi-C. There's a critical temperature where all compositions will mix. So we want to kind of be able to calculate this. We want to calculate these binodal curves, if we can do it, the spinodal curves, and we want to calculate that mathematically. And we'll see how to do that basically as a function of basically these changes of inflection points. So the second derivative and our first derivatives when they're basically equal to one another. So we will get into that next time. So I'll see you then. Thanks. If you have any questions. Bye.